afternoon, everyone. Today we will continue our discussion on applications of vectors, and we will be talking about scalar and vector projections. You will see that scalar and vector projections are not new concepts for you. We have discussed them. It's just that we did not introduce the terminology. So our objective is to introduce the proper terminology. We will start off by reviewing the dot product. What was the dot product? Well, when two geometric vectors were given, the dot product was nothing else but magnitude of A times magnitude of B times cos alpha, where angle alpha is nothing else but the angle in between vectors A and B. Then what we did, we threw these vectors into a coordinate system, into a 3D coordinate system, where vector A can be written as A1, A2, A3, and vector B, you have both of them here. Vector B is B1, B2, B3, the components of vector B. So when I write them like that, we took a lot of time to prove that the dot product of A and B is given by A1, B1 plus A2, B2 plus A3, B3. Of course, the formula can be adjusted accordingly when you talk about R squared, the 2D coordinate system. Okay, so let's see why these dot products are useful. Let's start talking about projections. I want you to see how I will construct a projection of a vector on another vector. I have here two vectors, vector A, the black one, and vector B, the blue one. First thing that I want to do the projection of vector B onto vector A. How do I do that? So projection of B onto A. That's the first thing that I want to do. This is what I'm going to do. From the head of vector B, I'm going to drop a perpendicular line to vector A. Do you see my perpendicular? So from head of B, perpendicular to vector A. The segment that I'm getting there, the vector that I'm getting there, it's called nothing else but the projection of B, the projection of, there you go, it's right here. So this is nothing else but projection of vector B onto A. Now, can I use the same procedure to project A on B the other way around? Can I do that? So what I want to do now, I want this time to project A on B. Well, I should follow A onto B this time. I should follow the same procedure. What was the procedure? Do you remember what the procedure was? We said, from the head of, this time vector A, draw a perpendicular. I want to draw a perpendicular to vector B, but I have a problem here. What is my problem? Vector B is not long enough. Well, that shouldn't be a problem. I will extend vector B. Let's extend vector B. I only need the direction. Okay, so I extended vector B. So now what I can do from the head of vector A, I draw a perpendicular to the direction of vector B. Is it perpendicular? It's pretty good. And now to make it just perfect, I'm going to show that this is perpendicular. Don't forget it was perpendicular. Good. So how did I get in the first case my projection of B to onto A? Well, I joined point O with where my perpendicular hits the direction, the vector, or the direction of vector B. So there you go. This must be a little bit too long. Make it shorter. This, the red one. Do you see the red vector there? That is nothing else but projection of vector A onto B. I'm gonna send this to the back. There you go. So we still see vector B. Okay, and this can go to the back as well. Order send to back. Good. I don't need to see that. So again, I'm gonna do this. The red vector and segment represent the projection of A onto B. So this is how I construct it. Now, let's talk about their magnitude. I'm going to put here point P. This is my point P. And how about N here? So don't forget, OP as a scalar is nothing else but, guess what? The scalar projection of B to A. Can I find it? Can I find OP? That's my question. Can I find the scalar projection of B on A? Can I find that? Where have I seen this before? Well, we've talked about that particular segment when we introduced the dot product A and B. We said, oh, I know this is magnitude times cos alpha. Now, if you look in that triangle, this is angle alpha. Cos alpha is cos B times cos alpha. We already know that that's nothing else but the magnitude of OP. Not a secret. As a result, I can write the scalar projection of B onto A as dot product of A and B divided by A, by magnitude of A. Right? Sure. Now, the other way, the other one. What do I want there? I want to see projection of A onto B, which is, on my diagram, I want to see magnitude of ON, which is the scalar projection. Quite obvious why we call it scalar. Where have I seen this before? Well, again, when we talked about the dot product A and B, is again magnitude of A times magnitude of B times cos alpha. Now, what do I need? I need to get to the segment ON. Well, if I want to get to the segment ON in the same triangle as before, A cos alpha, this is a procedure that we already did, A times magnitude of ON is nothing else but magnitude of ON is nothing else but magnitude of A times cos alpha. There you go. So I can replace A times cos alpha by ON, the quantity I'm looking for, times magnitude of B. As a result, the scalar projection of A onto B will be given by ON dot product of A and V over this time magnitude of B. Please notice that the two scalar projections are not the same. One is divided by B, of course, the other one is by A. Good. So that was a story about scalar projection. Now, let's talk about vector projections. What I need to do, and it shouldn't be a surprise for you when you talk about the magnitude of OP for the scalar projection, now to talk about vector projection, guess what I need to do? I need to define the vector projection is nothing else. The vector projection is nothing else but vector OP in this case, vector ON in this case. That shouldn't be a surprise. Now, I know the magnitude of these vectors. How do I make them vectors? Do not forget, OP has the same magnitude as, same direction as vector A. So, it has to be related to vector A. Now, do I know the magnitude of OP? Sure, I know the magnitude. It's right here above. It's given by this expression. Now, what I have on the board is indeed now a vector. However, I cannot multiply by the whole vector A. I have to multiply by a unit vector that has the same direction of A, but doesn't change the magnitude of OP. So there you go. I will multiply by magnitude of A, by vector A divided by magnitude of A. So why do I do that? Because the magnitude of this is a unit vector, and this is extremely important for me. So I can rewrite OP as vector OP as dot product over magnitude of A squared times vector A. Good. Now I'll do the same thing for ON, and that will give me something like that. But this time I have to, do not forget, ON is in the direction of vector B. So in order to get the vector, a vector here, I will multiply by vector B, but because I do not want to change the magnitude, I will also divide by the magnitude of vector B. This is again what I multiply here is a unit vector. So there you go. The vector projection will be given by. Do not memorize the formulas, understand the process. Now, as an application in class, we will be talking about direction cosine. That's important, an important topic, and we will cover that in class. There you go.